Welcome, everyone. We have partnered with Detroit Tech Watch once again for another awesome discussion. Today, we're talking about 4 types of check-in with expert guest Richard Feldman. Before we get things started, I'm Ryan Nico. I am the Community Associate for Collider, a community of software professionals and business leaders who connect and explore innovative solutions, breaking down barriers between technology and business. And we would love for you to join the conversation. You can learn more about that and how to get involved at the link that I will drop in the chat. It's going to be collider.altimetric.com/community. Collider is powered by Altimetric, which is a leading digital business enablement company, and it drives transformation and achieves business goals for clients all over the world. If your company is looking to get unstuck and take your digital strategy to the next level, please let me know. Our team's growing fast, so don't hesitate to reach out if you're open to new career opportunities. So Arnario and Mike, please take it away.
Awesome. I'll go ahead and take this one really quick. Yeah. So Richard, probably doesn't need much of an introduction, but he's really into types. He's really into Elm, and so I know you're doing some other cool stuff too. Honorio was mentioning the rock language, which is super exciting. So exciting stuff. I'm gonna let you take it away, man. The 4 types of type checking. Go for it.
Cool. All right. Thank you. Let me dive into it. So I since this isn't like a conference talk and there's like a pretty small number of us here, I've kind of like laid this out like a conference talk because that's kind of my habit. But please feel free to just like pause and ask questions, and we can just like go off on tangents. We don't need this to be like a strictly like, oh, I'm going to present. We're just going to go through all the slides and then we'll have 5 minutes for Q&A, right? It's like we don't need to do that. It's a meetup. We could just be casual about it. So yeah, if you have questions along the way, I don't think I'll be able to see the chat, but like feel free to just like speak up and be like, hey, I have a question, or like I have a want to talk about something. Please feel free. Okay, but having said that, I'm gonna just launch into it. All right, so this is the 4 types of type checking. I'm Richard Feldman. Okay, so I'm gonna start by saying what I think are pretty much indisputably the 4 types of type checking, or at least I'm going to categorize all type checkers into one of these 4 groups. One is no type checking. That one sounds straightforward, but it turns out it may not be what you have in mind when you think of no type checking. The other is runtime type checking, which is what maybe a lot of people think of as no type checking. Another is build type checking, and then the other is both, doing both runtime and build type checking. For the purposes of this talk, I'm going to try to largely avoid terms like static versus dynamic. Those can mean different things, or like strong versus weak. I'm really just going to kind of break it down into these 4 categories. For that is that these are empirical. You can look at a checking system and ask, is it running at runtime? Is it running at build time? Is there neither? Is there both? It's very easy to like concretely say which one is, and like static and dynamic, strong and weak, the definitions sort of vary depending on who you ask. So these are at least straightforward. Okay, but I'm going to also break down, like in terms of these 4 different types of type checking, how do they interact with questions like, how helpful is your type checker or lack thereof? How are your feedback loops? What's the performance like? And also, what's the potential of each of these 4 different systems? There's one system that I think has more potential than the others, and you might be surprised which one I conclude by the end of this. Okay, so let's start with helpfulness. This is no type checking. This is like a punch card from back in the day where you basically would like write out, like, here are the instructions I want the machine to execute, and you would put them into the machine and it would execute them. There's no type checking. It was just like, just go, just do one instruction after the other and just let the chips fall where they may. Here's an example of what that sort of like looks like. So I'm going to write pseudocode here. This is not any particular programming language, but let's say we have like an if, some condition, then x equals 5, else x equals hello world. And then we're going to say that's the end of our conditional, and then run answer equals x minus 3. So if we have a no type checking world, obviously this is going to do something different depending on whether some condition is true or false. If it's true, then we're going to get x minus 5, 5 minus 3. And if it's false, we're going to get hello world minus 3. So what's that going to do in the hello world case? I mean, in the 5 minus 3 case, we can know what the answer is going to be. It's going to be 2, but like what happens in like, assembly code, for example, if we run this? Well, in this like punch card or like assembly world, we probably one of 2 things will happen. One is, so basically what this is going to do is it's going to say like there's a pointer in that slot. And so we're going to subtract 3 from that pointer and then treat that as the answer from then on. So that pointer is going to be some number. It's probably going to be a pretty large number. So one thing that might happen is we get x minus 3, like x being set to hello world, is equal to this gigantic number of like random digits that happen to be in like memory representing that pointer. So just total garbage. Nothing like, I don't know what we expected here, but definitely this was not what we wanted. That's if we're lucky. If we're unlucky, what we'll get is a segmentation fault, because now we have a pointer that is like totally invalid, and then maybe like, you know, we're trying to access like memory if we end up trying to dereference this answer because we're treating it as the string rather than the integer. All sorts of bad things could happen here.
I think
so this
if
is
you get
like
the seg fault, you are lucky though, because then you know you've got a problem.
right, that's true. At least the seg fault is feedback, right? The incorrect number is not any feedback at all. It's just wrong by a lot, probably. So this could just happen, right? I mean, this is like back in the day, this was programming. Like you would just have that. Now, fortunately, today we have some, you know, niceties, like some actual type checking that, you know, goes beyond this sort of no help at all world. An example of this is Python. So in Python, I translated the pseudocode to Python and ran it, and Python gave me type error, unsupported operand types for minus, str, and int. So in other words, like you can't do minus on string on one side and int on the other side. Cool. That's much more helpful than just super getting the wrong answer or giving me a segmentation fault. Now in TypeScript, I also translated this pseudocode to TypeScript, and it gave me a different error at build time. The left-hand side of an arithmetic operation must be of type any number big int or an enum type. I don't think this is as helpful as what Python told me. I don't really know, like okay, yes, I agree with you. Like, sure, that's a rule, but like, what does that mean? Like, I think that x is a number. I have to like now trace through my code to figure out, oh, I see, I was setting x to be a string there at one point, so it wasn't like a number. Okay, fine. But this to me is less helpful than what Python told me in terms of the error message. I think Rust does a little bit better than these. So it's expected integer found string, and it even says like expected due to the type of this binding. Now that like maybe is or is not helpful. Like if I'd actually written out a type on that binding, then that would have helped. But here it's like, well, let x. What do you mean? Expected due to the type of this binding. That doesn't help me. So this is not like the most helpful thing, but I would say it's at least more helpful than what TypeScript told me. Of course, the gold standard, you know, I'm Richard Feldman. I'm here to give a talk. I cannot possibly get through a talk without talking about the gold standard for high quality error messages, Elm. This is what Elm gives for this pseudocode. The second branch of this if does not match all the previous branches. The second branch is a string of type string. All the previous branches result in number. This is about as much information as I could possibly want about this error. Worth noting that this error is actually a little bit different in Elm than it was in TypeScript or in Python, or in Rust for that matter. Elm is actually complaining a little bit earlier. It's saying like, okay, I'm not complaining about the type of X. I'm actually complaining about the fact that this if conditional in and of itself is inconsistent. Like one branch is returning 5 and the other branch is returning a string. Part of that is because Elm is a pure functional programming language, so you wouldn't actually write x equals 5 in both these branches because that would be a mutation, which you don't do in pure functional programming. So it's a little bit different because of that. But fundamentally, I mean, it's really breaking down what the problem is for me here. It also goes a little bit further and says, hint, all branches in an if must produce the same type of value. This way, no matter which branch we take, the result is always a consistent shape, which is exactly the problem that we run into when we run this like through the machine code thing, that an inconsistent shape, you know, depending on which branch we take. And it's got a link to like learn how to, you know, if you want to actually mix these types. And then it also has a hint, which in this case is actually not that helpful. Using string to int to convert it to an integer. I mean, yeah, that's not really the problem here. The problem is we've just made a mistake. Okay, so these are all sort of part of the user experience of like getting an error, right? We have like Elm is like, okay, second branch is a string of type string. All the previous branches result in element. That's the problem. Python is like unsupported operand types for minus, str, and int. TypeScript is like expected integer. Sorry, Rust is expected integer found string, and then TypeScript, you know, left-hand side of an arithmetic operation must be of type any number big int or an enum type. Of note, the user experience of these error messages is not really dependent on, like, at least not innately, on when the message came out. Like to me, the most interesting parts about these messages is like the wording that they used and like the information they provide, like string and number versus like not mentioning it, just saying like, here's what I expected, explaining that like the problem is the inconsistency in the if branches versus this, the problem is with minus. Like Elm tells us about the problem a little bit earlier than the others do. Now, also worth noting, though, that some of these error messages are more or less possible depending on when they're coming up. Like if we have the Elm error where it tells us about the branch and the if thing, that would be pretty hard to do in Python, because for Python to know that that's the problem, it needs to somehow do that analysis of like the entire if expression at runtime, which it doesn't necessarily know about. It's just like, well, I was trying to do a minus on a number and a thing. I don't know, like, what am I doing? And it's when it does an if, it's just looking at the conditional and then taking one of the branches. It's not going back and looking at the other branch in case it was like the wrong type. It's only doing one branch at a time. So I don't think you could give that Elm message in Python land, but that's not to say that that's like what makes Elm better. It's more that like what Elm does with that information that it has is, to me, what makes for the nicest user experience here. I'm reminded of the user experience of like putting in like passwords on a sign-up sheet, like on a sign-up form on a website. Like the nicest thing is when it gives me a bunch of context. It's like, oh, your password, like, okay, it does include both upper and lowercase characters. That's good, but it does not include at least one number symbol, and it's not 8 characters long. Some forms will tell me this, and when I do that, like, I'm like, okay, cool, thanks. I appreciate you're telling me the rules and also like what the problems are and like what I'm doing okay and what's not. Like a less good one is like invalid password, minimum length 8, minimum, non-alphanumeric characters 1. That's like the same information, but it's just not formatted as nicely. Or there's just like, I'm not even going to tell you what's wrong. It says password is not valid, deal with it. And then the worst is just when you just get something where it's like, something is wrong, I don't know, like there was a bad thing, figure it out. This type of user experience stuff is really just kind of programming. I mean, it's just engineering. It's not like it's innate to any particular like paradigm or language design or anything really. I mean, this is just like, how much time did we put into formatting the error message? How much time did we put into like collecting context? Like, oh, your password, some of these things are correct, some of these things are not correct, versus just like, we wrote one function that just returns a Boolean, is the password okay or not? And then that's all the feedback we can give to the user. Now that I spent some time working on a compiler, I can appreciate this more, that it's just like, yeah, any language could improve their error messages. It's just a question of like, do they decide to do this? Just like any website could choose to improve their, password validation experience. Some websites do, a lot of them don't. Same thing with programming languages. Some programming languages put more time into their error messages and, reap the benefits, or the users reap the benefits in terms of UX. A lot of languages don't, or a lot of compiler implementations don't.
Yeah. I was going to say, Richard, I remember years ago, somebody pointed out, and it's always held true, the easier it is for the end user, the harder it is for the developer. And since most developers don't have any time at all, that's why you get stuff like where it's like, oh, just shove it out. I don't have time to fix this and make it nice.
I think that's a good point. And I do think that's more true of like the time crunch thing is more true of like this than this. It's like this.
Oh, yeah, I agree.
Usually
yeah.
It's like Python's probably had this error message for a very long time and like probably has not changed it. I bet they could make even this, like there's some obvious improvements you could make to this error message right here, in terms of like just making it a little bit clearer, like minus colon. I'm sure they could do better than that. But nobody's putting the time into it because they're, it's, I don't know, it's that's how it's been, and people are like, it's good enough. Okay. So some of the trade-offs here in terms of like error message helpfulness when it comes to the 4 different types of type checker is like at build time, there is more code information available. Like Elm's like if disagrees with else branch, that's only really possible if you're able to like analyze, the surrounding code. Can't really do that just at runtime if you're just taking one branch at a time. You don't know what the other branch was at runtime unless you want to like go back and like traverse the all the other branches just in case. That's not really going to work out. But at runtime there is more value info available. So in other words, you could write an error message. I don't know of any languages that do this, but they'll say like can't subtract then the actual string hello world from the actual number 3. To be fair, I'm not sure if that's that helpful when it comes to type mismatches. Like I mean, really the key thing that I need to understand is it's like this thing and this thing, there's a mismatch between these 2 variables. Do I necessarily care what their runtime values are? I don't know. I don't think that really helps me. But worth noting, that is something that you could do with runtime type checking that you can't do with build time type checking. Another question here, though, is of course timing. So at build time, we find out about the error message like as soon as possible. But as we'll talk about later, that also means we're sort of confronted with it earlier, which has pros and cons. Another possibility is we get the error message at runtime, like we did in the Python example. But it's also worth noting that another possible time that we could get this error message is never, not at all. It's entirely possible in some cases that this error message might just not come up. So like this is a conditional, right? What if, as it turns out, some condition is just never false? It's just always in every single code path that ever gets taken by a real user in practice, x is always equal to 5 as it happens. And so the fact that we had this problem, this, or this potential problem, never really materializes in practice. It never actually harms anyone, any actual end users. Then you could argue, well, that's perfectly fine. It's harmless. It doesn't affect anyone negatively. So, why bother taking the time to like fix this build time error that could have just been not a runtime error, but rather no error at all? So that's sort of like a philosophical question. There's a related question here when it comes to serialization, or like a related like philosophical design question. So in JavaScript, this is how you would do like the typical way that you would parse some JSON. So you're like JSON.parse, you give it a JSON string, and that'll give you back, let's say, a user. Now, when I say it'll give you back a user, what I really mean is that JSON.parse will give you back some object that represents what was inside that JSON. And hopefully, if everything worked out, that it happens to be in the shape of a user. It might not. There might be some fields missing. There might be some fields that have like one type in the JSON and then a different type the way that I'm using the user object later on in my program. JSON.parse doesn't really deal with any of that. It just says, I'm going to give you an object, and then you can use it and just find out what happens with it. Rust does things differently. So in Rust, this is a really common, like the most common way that people would deserialize some JSON is they would first write out a type declaration for what user looks like. So let's say it's name and email. There'd probably be a lot more stuff in there, but this is a small example. And then at the top, they would write derive, serialize, and deserialize, which is something that comes from this library called serd, which is short for serd, so like serialize, deserialize. And when you add that annotation to the user derive, serialize, deserialize, it sort of generates an automatic JSON like serializer and a JSON deserializer for this user struct. And then in order to actually get a value out of this, you would say, let user : user. So you have to put in the actual explicit type of the user, even though Rust often has type inference. In this case, you actually would need to annotate it so that it knows like to use users deserialize here. Then you would say serd underscore JSON, which is the name of the library, : from stir, and then pass in the JSON, and then dot unwrap. So the unwrap at the end is another difference between the Rust version and the JavaScript version. What that's doing is basically saying, this from stir is not giving me back an actual user. It's giving me back a wrapper around the user. And that wrapper is called a result in Rust. And basically that wrapper says this might be a user, but it also might be a decoding error. Like if we didn't have a name string field and an email string field in there, I'm going to give you back an error rather than giving you back a user. So this has pros and cons compared to the JavaScript approach. On the one hand, once you get one of these users back after you've unwrapped it and said like, okay, so unwrap here will basically like throw a runtime error if it's not an actual user. I know from this point on in my program that my user value here is actually going to have a name, which is a string, and an email, which is a string, like for sure. There's no chance that it won't. But if it doesn't have those, well, even if I don't end up using those fields later on, like for example, let's say I've deserialized the email field and that was an error because the JSON didn't have an email field, but I never actually used the email field anywhere in my program, it's still going to error. I'm still going to get either a runtime crash or whatever else bad thing is going to happen. Whereas in the JavaScript version, that wouldn't. So again, it kind of comes back to this philosophy of like, if an error is never going to happen in practice, do you want to be forced to handle it anyway? So there's also a question of what is the sort of like timing? Oh yeah, question or comment?
I was just going to ask Richard. I'm sorry, I keep talking over you. That's why I raised my hand that time.
Oh, you're good.
I was going to ask the result, the wrapper. It's kind of like a maybe monad, right?
Pretty much, yeah.
That's my recollection of Rust. Yeah, okay.
It's like maybe, but there's a little. It's actually more like either, if you want to use like the Haskell equivalent, in the sense that it's either there or it's not, and there's an error message in addition to like the fact that it's not there.
Yeah, I mean, it's how they get around not having a null, right?
That's one way to look at it. I guess another way to look at it is that sure, we can go with that.
Okay.
For simplicity's sake,
Okay.
sure.
I'm sorry. I mean to take us
Yeah.
down a rabbit hole. I just,
No worries, no worries. No, I requested rabbit holing, so let's, I appreciate it. And others feel free to dive in too.
Yes, please.
Okay. Right. So it could be, just like with the type mismatch on the conditional, the field error could be reported immediately or eventually if there's a problem later on down the line. And this can be really nasty when this happens. Like if you have you decode some JSON and it seems like everything's fine, like with JSON.parse, but then it turns out, much later on down the line that something was wrong. It can be pretty annoying to trace that all the way back to oh God, it was the JSON that was wrong, as opposed to having it right away. It's oh, there's the problem. The JSON was missing this thing. But of course, it is possible that it would never come up. So really, there is this philosophical question in both of these cases with serialization as well as with type checking in general. If it's not causing bugs, do I care? Should I do anything about it? And one argument is to say no, I shouldn't care. If it's not causing any bugs right now, for real users, don't spend time, preemptively solving these problems. That's over engineering. I should just go work on other stuff and make other improvements to my program with that time I've recouped. And then the other argument is well, yes, I should, because just because it's not causing bugs now, it's just waiting around until the first time it burns someone. It clearly could if this, if the stars align and this conditional actually gets taken, or somebody else writes some code that actually does try to access that field that's missing on the JSON or whatever the case may be. It could end up breaking something in the future. And since we know about it now, let's just fix it now before it actually becomes a problem for someone. Different people might have different values around this. Personally, I tend towards the latter, as long as it doesn't take that long to fix. But I definitely appreciate the fact that people have lots of trade-offs they're dealing with, one of which is time pressure. So I don't think there's one answer here, but I do certainly have a preference. Okay. So that was helpfulness. Let's talk about feedback loops, because this is definitely another big factor, especially when time pressure comes into consideration. So this is the obligatory classic xkcd.com/303 #1 programming excuse for the domain slacking off. My code's compiling. I forget when this comment came out. I mean, it was, I think, more than 10 years ago now. I could look that up, but it's pretty much, it would have worked in the 80s. I mean, this is just ever since we've had compiled languages, they've taken a long time to do it. And I think in some cases, the compiling part is slow because of the last step, the code generation step. But very, very often, it's also taking a long time to type check things too, depending on the language. Some languages are a lot faster at that than others. But certainly, people definitely spend plenty of time still today, even on this very fast Mac M1 machine, waiting for a code to compile. I certainly do. And the big problem with this is, in addition to wasting wall time, is it just destroys your flow state. If you're trying to do something in a fast feedback loop and try something out and try something else out, and you care about the runtime values, you're trying to get a test working, or you got some behavior that you're trying to experiment with and try different things, this is just a total disaster for that. It really just wrecks your ability to get in the zone and just keep going when you have to stop and wait for several seconds for your code to get working again. It just especially, I mean, every single time I hit compile and I'm just waiting and watching the loading spinner, part of me is there's a web browser one alt tab away. I could just go just real quick, go look at something on the internet or check my email, or and then before you know it, 15 minutes later, you're oh yeah, wasn't I doing something? Oh yeah, I should go back and this is really, really extremely bad. And I think as an industry, we make jokes about it, but it's actually extremely bad. I mean, it's funny, but it's also it's kind of sad that we actually let ourselves get destroyed by this so often. I personally have this thing where every single year, the language that I use for the main thing that I'm working on right now, which is a compiler, is Rust. And every single year there's a state of Rust survey, and they ask what things would you like to change about Rust? And I think there's 5 fields, what are the top 5 things? And I just put faster compile times, faster compile times, faster compile times 5 times every single year. This is a huge deal. And I think as an industry, we've just sort of grown to accept it for some reason. But I think it's honestly a big part of the reason that in the 90s, we saw this sort of plethora of languages that don't have like build time type checking sort of come into existence is and gain a lot of popularity, specifically JavaScript, Ruby, and Python. They don't have this. Like they're not sitting around waiting for their code to compile, and that's a huge deal. There's another aspect to feedback loops, though, which is blocking errors versus non-blocking errors. And this also has to do with flow state. But yes, question, raised hand.
I was going to say, I remember, and I'm going to date myself. I remember back in the day, C++ had an option to precompile headers, which the idea of it was to speed up your compilation. Because your headers would very rarely change. It was the source code that would change, right? And so I forgot what the compiler switch was, but they had this option to precompile your headers for exactly that reason. I just wanted to mention that.
Yeah, and I mean, like there's also a lot of like caching, right? Of like try to avoid recompiling things as much as possible, which helps in a lot of cases, but also like especially if you're switching branches, like it just a lot of it's like, oh, okay, back to square one with the caching, and some languages are better at caching than others in terms of like the granularity of the caching, like how much caching helps and all that stuff. I wish it was more effective than it than it seems to be in practice. But anyway, so compile times is one, but there's also just this question of blocking versus non-blocking, and the difference between this and compiling is that with compiling you're just waiting, but with these things it's like you actually need to take an action before you can proceed with what you want to be doing. So here's an example of this. So this is the Go programming language. And one of the things, Go is the only language I know of that does this. Go has a compile time error, a build time error, if you have an unused variable. So here it says the variable C is declared and not used, and that means it's an error. It's a blocking error. What that means is you cannot run your program until you deal with the fact that you have an undefined variable here, or a variable here that's unused. Now, could you run your program? Like this is clearly just purely a design decision. Like there is absolutely no technical reason that you need to be blocked from running your program. Go is perfectly capable of compiling a program with a variable that is not used. Hint, it works exactly the same way as a variable that is used. There's just nothing that ever gets assigned to it. But they have chosen not to allow that. So the program could run, but it's blocked from running. Now, this means, among other things, that the cost of experimentation goes up. Like if I want to try out, like for example, I've got an idea for like a new API design, like as in like or a new interface design for how I want to like structure my program. I want to try this out real quick. I make some changes and I'm like, okay, I want to run the program to see if it still runs as fast as it did before. Like one of my concerns maybe is I think the code's nicer, but I'm concerned about the runtime performance. I want to try it out. Or maybe I'm trying to performance optimize something and I'm like, you know what? I can see a potential thing that might run faster, but it's going to require a bunch of changes and stuff. And some of these things will be like unused variables as a result of this, but that's okay. I just want to run it and see how fast it runs and see if it actually improved performance. I don't want to spend time cleaning these up unless it actually made things faster. And if my benchmarks say it was slower, I'm going to be really annoyed that I was forced to clean these things up and fix these problems, basically for code that I'm going to throw away anyway, because it turns out they were actually slower. This is just a downside of Go, of the approach that they've chosen to make this a blocking error. Similarly, if I'm doing some sort of like test first workflow, it's also disrupted. But this is not just Go. This is build time type checking in general as a general rule. If I let's say I make a bunch of changes and I'm like, okay, I've made all of the local stuff that I want to test for this performance thing or for this test that I want to run. I've made that type check. I still can't run it because all of those breaking changes that I made have caused a bunch of errors in other parts of my program. Now, even if I'm like, I want to run tests that do not touch the rest of that program, or I want to run a benchmark that does not affect, has nothing to do with the rest of this program. I just want to isolate this one thing and just try this out and see how fast it runs. I can't do it. I'm blocked from doing that. Now, I would not be blocked in like a Ruby or a Python or a JavaScript, but in a language that traditionally, at least in a language that has build time type checking, the norm is that I'm blocked from doing that. This workflow is just totally, unavailable to me. And I think this especially like this disruption of like test first workflows where I'm like, I would like to write a bunch of test examples, verify that they run and get the wrong answer. Even if there's type mismatches, I don't care. I just want to see the tests like be read, and like because the values are wrong, not because there's like type mismatches potentially somewhere completely unrelated elsewhere in my program. And then I want to go through and make each of those tests turn green one at a time. Again, maybe the entire time while there's known type mismatches elsewhere in my program, potentially for workflow reasons, because I'm like, I want to get this code working and verify that the approach actually works. And if and only if it does, then I'll just go and fix the other things. But like, I want to do this first and then go fix the other things. Again, that workflow is just often closed off. I have to go fix, I have to do cleanup before I even know whether I want to commit enough to have that stuff cleaned up. I think this is part of the reason that even though literally the book Test-Driven Development uses Java as an example, Java is not the language that's like most known for TDD. I had a suspicion about this, and then I ran a completely unscientific Twitter poll to confirm it, and I ended up finding that people said basically what I expected, which is that Ruby is the language people most consider to be like where people are the most into TDD. That was my perception. That seems to be like at least 570 Twitter poll respondents impression as well. And that's among the top 3 most popular programming languages, which are Java, JavaScript, and Python, and Ruby. Now, granted, like Java was, also quite high on that list, but I guess like this wasn't a stack ranking. People had to pick one. So maybe if I took Ruby out of the list, other people would have picked JS and Python over Java. I don't know, but certainly I was not surprised to see Ruby with, almost 60% of the votes. And I think a large part of this is that in Ruby, that workflow is completely undisrupted. You can write all of your tests. You can get each of them failing because the values are wrong, and then one at a time, just go through and make them pass. No matter what else is going on in the rest of your program. This is just a downside of build time type checking, at least the way that it's typically implemented today. Okay. And oh yeah, by the way, this also applies to like all type checking, like regardless of like error message quality. Like these error messages can be helpful, but they can also be, the downside is when they are blocking. And certainly like in Rust and in Elm, these are blocking. Worth noting that it's not to say that you can't have build time type checking as well as non-blocked workflows. So this is a type checker that's been added on to Ruby Sorbet, built by the folks at Stripe. And I want to zoom in on this one particular part of the Sorbet website, Gradual by Design. It says Sorbet works with normal Ruby. So you can keep using your existing toolchain, or from my perspective, more importantly, your existing workflow. If you want, you can run your Ruby code without invoking Sorbet at all and just get all your tests working. You can do that test first workflow as much as you want. And then afterwards, you can run the Sorbet type checker and see if your types are messed up, and like find out what else, like what are the cleanup stuff you want to do. But again, you have the option. You can do it either way. That's a big deal. And so when it comes to like blocking errors and non-blocking errors, if you can always run your program, then all of your errors are non-blocking, basically. Either you'll find out about them at runtime if you choose not to run the build time type checker, or you can find out about them at build time if you do choose to use it. So I think this is one of the reasons that people, I've heard people say gradual typing like this is the best of both worlds. So doing both runtime type checking and build time type checking. Like I talked about in the very beginning of the talk. Now, I can see why people say this, but there's more to the story. Let's put a pin in whether or not gradual typing is the best of both worlds and revisit that after we talk about performance. So, runtime performance of machine code is great. And I actually would go as far as to say it's superlative, because the fastest that your program can run is actually limited by your hardware. You cannot write software that is faster than what the hardware permits. That's just actually impossible. And what the hardware permits and what the hardware supports is machine instructions. So if you are doing punch cards or assembly code, like just writing raw assembly, which translates one-to-one into machine instructions, that's actually unbeatable in terms of performance, at least at a theoretical level. Now, granted, is a human actually capable of writing stuff that outperforms like a really well-done optimizer? The answer is basically like yes or no, depending on how complicated it is and depending on what's being optimized and stuff like that. But certainly you cannot do better than this, at least on theoretical level, than like machine code. So I know I haven't talked a lot about the of the 4 types of type checking, the no type checks anywhere option. performance is one case where that actually shines. It really is unbeatable. Like in terms of, how much runtime performance can you possibly get? When people use the phrase drop down into assembly, what they're referring to is I needed some performance like almost every time. And the way that I got that performance was I wrote a little bit of assembly code, and that let me get the performance that I needed. Even build time type checks, because they're sort of inherently conservative, are often too restrictive, and they won't permit writing code that is faster and does work and always works, but is not accepted by the type checker. And that's usually when people will resort to like dropping down into assembly to get it. So I know I haven't said much about it. It's mostly downsides. It is very unhelpful, but when it comes to performance, cannot be beat. Okay. Also worth noting though, these languages, C, C++, Zig, and Rust, these systems level programming languages, these are quite popular languages. Okay, Zig is more up and coming, I guess. C and C++ very widely used. Rust is, I think, other than TypeScript, maybe, like Rust and TypeScript are definitely the two most like rising in popularity, the fastest languages. And of note, TypeScript, I think we can all safely assume, did that because it's such a drop-in replacement for JavaScript. Rust is not a drop-in replacement for anything. It's like brand new, from scratch, like starting from square one, and yet it's like incredibly popular. It's probably going to be one of the top 10 most popular programming languages within a couple of years, if it's not already. All of these languages use build time checking only. One must assume this is because they didn't get the memo about gradual typing being the best of both worlds, because obviously if they got the memo about gradual typing being the best of both worlds, they would have by now introduced gradual typing, and they would also do runtime type checking. No, but I mean, okay, seriously though, why do they do build time type checking only? Well, the answer is performance. So earlier on, we talked about this Python example, this pseudocode where we had like x equals 5 in one branch of the if and x equals hello world in the other branch. And then if we run it and some conditions false, we take the else branch and we get this type error. So Python doesn't do any build time checking. So how did it know that this was like a string and an int at runtime? Because if we were doing this in machine code, as we saw from the earlier example, the machine has no idea what the types of these things are at runtime. That's why if we don't have type checking, we just get memory garbage or a seg fault. So how does Python know? Well, the answer is that it has extra runtime metadata and extra runtime checks. So when we write x equals 5 in Python, again, this is kind of pseudocode, but basically what we're getting in memory is not just the number 5. It's actually something more like an object that has a type field that says what type it is, and then the actual value. And then for the string, we have another type field which says string instead of number, and then the value is the actual string. And then when we do subtraction, it actually has a conditional. It's like first check to see if both of them are of the type number. If they are, then okay, do your subtraction. Otherwise, raise the type error that we saw. This is a bunch of overhead. Like this means you have more memory overhead for every single value in your program. Like number has more overhead, string has more overhead, and also every single operation on those has more overhead. Subtraction has to do an extra conditional to check the types. Every single operation is like that. One extra conditional for every single operation like this in your program to check the types. And if they pass the types, then the answer, after you tell the machine, hey, do the subtraction operation, you then have to wrap the answer back up in another one of these objects, taking up even more memory of type with the type field and then the actual value. This is why people don't write operating systems in Python. When you have like really performance critical things, or for that matter, games that have non-trivial performance needs, you just don't see it happening because this is just a ton of overhead that is necessary if you want to do runtime type checking. You have to have the types available at runtime, then you have to actually check them at runtime. That's a performance cost. So why do these languages do build time checking only? They don't want to pay that overhead. These are languages where performance is a top priority for them. And so if you want to be able to unlock the highest tier of performance, basically your only two options of the 4 different types of type checking are build time only or no checking, like assembly. That's it. If you want to do runtime or runtime and build time, you're going to be slower. That's just how it is. This is a fundamental limitation of the hardware.
I have a quick question for you. So do you know of any languages that essentially have this, the build time check, obviously like these, right? But there's some sort of a flag at build where you could enable runtime checking? I don't know. This is something I never really thought about before until this very slide and in your last little talking.
So 2 answers. One is spoilers. Spoiler alert. We'll get to that in a few slides later. second quick answer is Haskell has a flag that you can pass in called -- defer type errors. And basically what it does if you do that is anytime it gives you a type error, it will let you keep building. It'll like successfully build something that you can run. But if it'll basically like generate a runtime error like in that branch, like if you ever reach that code where the mismatch happened, then it'll crash. The spoiler is that that's what Rock does too, and we'll get to that later.
Okay. Cool.
Yeah.
Thanks. Yeah. No, that's awesome. Cool.
Yeah. Okay. So why do people do build time checking only from a performance perspective? Yeah, because like that's the way to at least asymptotically approach, the speed of machine code within the limitations of like what your type checker is capable of actually checking. Okay. So really, I mean, if you look at it like from a performance perspective, gradual typing, you have the slowness of build times, like you're waiting for your code to compile because you're waiting for the type checker, like you have a build time type checker. And you're paying the cost of like runtime performance too, of the runtime type checker. So the idea that like gradual typing is the best of both worlds is really only true if you're completely disregarding build time and runtime performance. Arguably, it's the worst of both worlds when looked at from that lens. So I don't think it's as simple as saying, oh, why don't we just have both? There's a very clear downside to not having to having both, which is that your build times get slower and your runtime gets slower. Okay, so we talked about helpfulness, feedback loops, and performance of all of these different combinations of the 4 different types of type checking. And finally, I want to talk about the potential. And like I said at the beginning, I think there's one of these strategies that has more potential than the others going forward. And I want to talk about like what that is and why that is. Okay, so to me, based on all these factors, like I know that when people talk about, different type systems and like different trade-offs, there's a lot of personal opinion. And there's like, I like the way that these things feel, or I like the security or the comfort of this or that, or the flexibility, the ergonomics. To me, along the axes that we've talked about in this talk, the best of both worlds is something where I get helpful errors, I want short feedback loops, and I want fast runtime performance. Whether those, when those helpful errors are, like part of that is like the timing, like we talked about, like how soon do I get the error? How soon do I get the feedback? Like short feedback loops. I don't want to be sitting there waiting for my code to compile forever. I also, want to find out if my JSON decoding failed as soon as possible. Oops. Hang on a sec. Okay. Technical glitch. Yeah. So in my mind, this is sort of the actual best of both worlds. The thing that I actually want is these 3 characteristics. So I've been working on this programming language called Rock. It's very much a work in progress. It's definitely not ready for production use yet, but if you're curious to see like where it is now, you can check out rocklang.org. But I do want to like tie all these things that we've been talking about into like some of the conclusions that I've come to for Rock, and like these sort of explain why Rock is designed the way it is from a type checking perspective. Rock compiles to machine code or to WebAssembly. So it's sort of, it's not compiling to a virtual machine or anything like that. So that means that it can compete on performance with things like, like Go and Rust and C++. It does have automatic memory management, so it's never going to be as fast as like Rust or C or C++ or Zig. But our goal is to be like, in that same ballpark as like Go and Swift, and hopefully faster. And we do build time type checking. We do not do gradual type checking. And part of the big reason for that is that runtime performance goal. This is one of our error messages. So this is a type mismatch. This if has an else branch with a different type from this then branch. The else branch is a string of type str, but then branch has type num a. All branches in if must have the same type. If this looks familiar to you from the Elm error message that I showed earlier, that's because Rock is a direct descendant of Elm, and we very much want to live up to Elm's like type error quality, which I again consider to be the best in the business. And so a lot of these are just like pretty much direct translations of how like Elm does things, because I think Elm does a great job, and we want to do a great job too. One thing that's different though is that at the end you see like, okay, 1 error and 0 warnings found in 150 milliseconds. You can run the program anyway with rock run, and then the name of the I was doing this on a Hello World example. So what does that do? So rock run is basically a way to say, okay, I know that there are like problems in my program, but I have decided that I, for workflow reasons, want to execute it anyway. Also, you can do this with tests. That doesn't work yet, but it's the same basic logic under the hood. And so what the compiler does is basically what I just mentioned earlier, with that Haskell can do with the defer type errors flag, except it just like does it automatically, and not just with type errors. It's with any kind of error. So anything that would be caught at build time. So type mismatches, but also like naming errors, where like I wrote a variable that is like the incorrect name, is like a typo in it, or certainly any like unused warnings, anything like that, anything that could block you gets turned into and automatically generated as a runtime error where it would happen. Now, granted, this doesn't work great yet. So what actually happens if you do rock run is it's like, cool, all branches if all, like it still prints out the warning to like the error to tell you about it. And then it just says application crash with message invalid ret layout, shutting down. So like I said, this language is a work in progress. Like this is not, the UX that we want to end up with. This is just like where we are right now. But it did actually build and run the program. So we do have that part working, even if like the actual UX is like not, good yet. I don't think it'll ever be quite as like sort of smooth when you're doing it in this mode as something like Python would be, like in terms of when it actually crashes. But to be fair, the whole point of this is that when I'm doing this, the reason I'm doing this is because I don't think any of those branches are going to get taken in what I'm going to try out. I want to try out the stuff that works. I'm not in it for like, oh, surprise, this didn't work. I'm like, well, I think I can avoid those for what I'm doing right now. And I don't want to be blocked because I don't think I'm going to run into those things. So hopefully we can get to a point where at least the UX is reasonable, and then it gives you that non-blocking experience while still, giving you all of the information up front. So some like concrete goals that we have when it comes to like type mismatches. One is to report known problems as early as possible. So like if we know that something is definitely going to cause a problem if you run the program, or at least like if any combination of user inputs gets you there, report those as early as possible. In other words, at build time, but never block you from running the program or from running tests. Just always support that so that if that's your workflow, you can just do it and it'll work. And then the other part of this is like build so fast it feels instant. So we do print out the build time, like how long it took to run these things. So like 115 milliseconds, that's not like the fastest thing in the world, but it's fast. And hopefully we can keep that that low for like as programs get bigger through a combination of caching, and also like there's even more performance optimizations that we haven't yet implemented on this thing. So definitely we're hoping that like at least for rock, although there is more work being done at build time for sure, if we can keep it low enough that it doesn't break your flow state, and it's just something that's just like, okay, I press enter and it basically gives me the feedback, it feels instantaneous. To me, that eliminates that entire downside. I don't really care if it's 100 milliseconds versus 0 milliseconds. Like as a human, that's not long enough to like distract me and make me want to go, open my browser. But I do care if it's like, 100 milliseconds or like 1 second versus like 10 seconds or, a minute plus. Hopefully we can get so that like you're never looking at, builds that long. Okay, so another aspect where this comes up is deserialization. So we talked about this from the perspective of like in JavaScript, you just say JSON.parse. That means that if you're going to find out about problems, you're going to find out about them later. You're not going to find out about them right away. In Rust, you find out about them via unwrap. So you'll find out like right away if there was a deserialization problem and it was not able to turn the JSON into this user struct, then you're going to find out about it as soon as possible. But it does have the downside. Obviously, you have to actually like write out your types, ahead of time. Like in JavaScript, you can just say user equals blah, blah, blah. But there's like another factor here that we kind of didn't talk about, which is what happens when you have something else like protocol buffers, like you're not doing JSON. So in JavaScript, if you want to use protobuf, like protobuf is a binary serialization format. So unlike JSON, when you serialize to protobuf, it's like really, really tightly packed in the bytes. So it's like a much more efficient format, which is great if you're sending a ton of these. Like, I think the reason that Google created this was because like they realized that it was costing them like millions of dollars to use like bigger serialization formats because they just do so much, data serialization, deserialization between all their servers. But the downside is that you cannot get away with this JSON.parse here because you just don't have the information of like what's in those bytes. You can't just turn it into an object when all you've got is a string of like ones and zeros. You just don't know like what fields are or aren't. You don't know which things are numbers and which things are strings because that information is just not in those bytes. You're just expected to know what they are. So even in JavaScript, like you have this protobuf.js, you basically are doing something that looks kind of like Rust's, Sirdi, where you have to like write out, okay, I have, this thing, which is a string, and that thing, which is a string, and something else, which is a number. You just have to write all that out, even in JavaScript, despite the, the runtime type checking and all that, just because that's necessary for the format. Okay, so in Rock, we can actually do this. We can say result equals decode and the JSON text, and then JSON.format, which is basically equivalent to what you have in the JavaScript line. But using type inference, this actually ends up doing the same thing that Rust does. So the reason that this says result and not user is because just like in Rust, we're actually getting back a result that's either a user or a JSON decoding error. But unlike Rust, instead of having to like annotate this ahead of time and like write out, the types of everything, which granted you probably want to do anyway, but worth noting that you don't have to. This is all done via type inference. So Rock has 100% type inference, which means that basically the compiler can tell the types of every single type in your program. It always gets it right. It never makes a mistake on that. Okay, there could be bugs, but like unless there's a bug, it will never make a mistake. Like by design, this type system, is it's called decidable principal type inference. So never makes a mistake, and also you can never make a type more flexible by adding a type annotation to it. It always successfully infers the most general type that could be inferred for that. So basically, this is also a work in progress. Like this is something we have pretty far along. We don't have it like quite far enough that I could like literally demo it on my laptop yet. But basically it uses type inference to figure out like what are the types here, and then it just generates a decoder based on like this JSON.format thing. Worth noting that this JSON.format is not actually baked into the compiler. This is actually something completely described in user space. So if you want, you could give it like a protocol buffer format, which would, it'd be a little bit brittle for protocol buffers, but like you could do that and just say, okay, I'm going to infer the shape of my protobuf decoder based on the type of my user. You could just do that, or CSV, whatever. If your user's coming into CSV, anything you want, like this can work for all of it because the type inference is just general like that. It just knows the shape of your user based on build time type inference, and then it's able to couple that with the format that you want to decode into, and then it can just generate the decoder for you. Now, granted, this only works in the case of like trivial decoders. If you need to do some additional processing on it, like you might say, okay, this format gives me stuff in like not quite how I want to use for my domain modeling. You might need to write a custom decoder for that, or which you can if you need to. Or you might just say, well, I'm going to decode this into like a sort of temporary value for now. That's not quite what I want, and then I'll just like read the fields off of that and build my actual user the way that I want it. But the point is that just because we don't have this runtime type information that JavaScript has that allows it to do this like JSON.parse, doesn't mean we can't have the same ergonomics of that, or at least like equivalent ergonomics. Now, granted, this is a little bit different in the sense of like you do get an immediate error if a decoding fails, unlike in the JavaScript version. But again, from my perspective, that's what I prefer anyway. I want to find out about that as soon as possible. I don't want it to just like secretly snake through my program. Now, I grant that is a philosophical difference. Some would say they prefer for it to say, well, if it's never going to come up, I don't want to deal with it. But in my mind, like this is what I want anyway. I want the ergonomics of just being able to say, just decode the thing, figure it out with type inference, but also having it fail immediately if it's going to cause problems later. So this summarizing like sort of our goals when it comes to serialization. Make trivial encodings like this, just take no effort at all. Report runtime failures as early as possible, and just do this with any serialization format, not just like JSON, but also protocol buffers, CSV, whatever else, anything people can define in user space. Okay, and last, we have another goal of like fast runtime performance, which is kind of the third of the things that I got into there. I'm actually not going to talk about that here because I already gave a whole talk about this on how we do this in Rock. So this, if you're intrigued, take a look at this talk, Outperforming Imperative with Pure Functional Languages, and it sort of talks about like the various ways that we, techniques that we've used to get Rock to run really fast. But definitely only doing build time type checking is like a hard prerequisite for getting the performance that we've gotten out of it. Okay, so summarize, we talked about the 4 types of type checking in terms of like helpfulness, feedback loops, performance, and the potential. So from a helpfulness perspective, we talked about how like different error messages can be more or less helpful depending on like when they come up. how early, like do they show the build time or runtime? What does the error message actually say? How much context can it give you based on like the surrounding code? Does it know that at runtime? Does it know that at build time? We talked about helpfulness of like serialization and deserialization, which is like same kind of trade-offs there. Feedback loops, like how long are you waiting for your compiler? Is your build step blocking you from like running your program or running your tests? And then about performance and about like, there are definitely some ergonomics benefits to runtime type checking, but they do have a cost, an unavoidable runtime cost. And that's kind of why I think that I push back on the idea of the gradual typing being sort of obviously the best of both worlds. You do still pay in terms of like waiting for build times and also waiting for runtimes. So to me, putting all this together, I think of the four, the one that has the most potential is actually build time type checking only. And the reason for that is, as I hopefully demonstrated with like the Rock examples and why we're trying to go for these in Rock, is that the build time type checking downsides are more fixable than the downsides of runtime type checking or gradual typing, specifically around performance. There's just no way to get rid of the runtime overhead of having runtime type checking. It's just a bunch of overhead that you can never get rid of. You can make your build times a lot faster by designing the compiler to be really fast. You can make it so that it's non-blocking. You can make it so that serialization is trivial for trivial types, and then also still extensible and still gets you like the early feedback loop. And of course, as we've seen with Elm, you can make your type checker like really, really helpful, especially if it's being done at build time. That's sort of the like leads to like what I think is the actual best of both worlds. Helpful errors, at build time and also at runtime if need be, short feedback loops and fast runtime performance. That's what we're doing with Rock, and hopefully we will realize those goals. So thanks very much, and yeah, let's talk about it.
Awesome. What does Rock compile down to, Richard? Maybe you mentioned it. Hopefully I didn't miss it.
Briefly, yeah, I mentioned. So machine code, like it basically just produces a static binary. Also, you can compile it to WebAssembly if you want to. So
I did see that. Yeah. Okay. Yeah. That's awesome.
Good one.
That's great.
Yeah.
That's great. I have another quick one while I'm already unmuted.
I think Dan raised his hand.
Oh, sorry, Dan. Go for it.
No, that was just the clapping emoji. It was just clapping at the end.
I'm sorry. I thought you were raising your hand. I apologize. Go ahead, Mike. Yeah. I'm sorry.
Fun fact, fun piece of trivia. Dan is like one of the earliest contributors to Rock.
Oh, that's awesome.
Sweet.
Yeah.
Very cool.
Awesome. Like one of the first 5.
I think I may have met you, Dan, too, at one of the Elm comps too. Like your name definitely sounds familiar. So
yes, yeah, Elm in the Spring. I think I remember.
Elm in the Spring. Okay, that's what it was. Elm in the Spring. Yeah. I knew you were familiar. I'm like, oh man, I know this guy. So awesome, man. Cool. Good to see you. So my other question was, what are kind of the behavior and output of a runtime error in Rock, right? Like what are you gonna you said it's machine code, it's an binary executable. What actually happens? I'm just curious, right? Since you've compiled and there's no types.
I mean, okay, so without going on a huge tangent, which we can go on if you want me to, but the short answer is basically it'll like print out the error that like Python did and just exit the program. So it's like
so it does have enough information to say, hey, you tried to take a string and subtract an integer from it.
So the trick is that what we're doing is we're not actually checking that at runtime. It's more that at compile time, we see that there's a type mismatch at this site. And so when we get to later on, when we're like generating the output code, what we generate is just blow up if we get here. Like it always blows up.
All right. Yeah, I was trying to wrap my head around it because I had the question earlier that was kind of related to this. What about if you do get like some sort of a decoding error, right? Like we all know JSON can be wrong, right? That's like one of the most common things. What happens when one of those decoders like just fails on a thing? Like what do you get then?
So we do the same thing that both Rust and Elm do there, which is that we don't actually return you a user, we return you a result, which is like
I actually like that. Yeah, man, the Elm behavior there is just so nice. So okay.
Yeah, I think that's the way to go, because then you can handle it however you want.
Right. Cool. All right. Thanks.
Sure.
Well, I did raise my hand. I had a comment.
Yeah, go
I
for
think
it.
one of the dimensions of type checking that I think we'll all agree it's there. It's just it wasn't something you talked about. Was the importance of safety. I mean, if I got code that's critical, I've got to make sure this code, as much as I can, make sure this code is right. Then I want every possible check I can get on it. And most applications, you don't need that front to back. You just need it for certain sections. Like here's the section where I post this transaction or something like that. I got to make sure that's right.
Yeah, so I think there's an interesting. I definitely that's an argument I've heard before. I think that the reason I didn't talk about that, and maybe I should have, is that I think there's definitely a rabbit hole there that definitely gets more into the philosophical side. So let's say you're doing something that's really safety critical. Let's say it's NASA, for example. One argument you can make there is you need to use every tool at your disposal to verify the safety. So it's not just like maybe you want runtime and build time, or if the performance can take it. And on top of that, you want to write some proofs. And on top of that, you want to use fuzzing and like property-based tests and manual QA. There's just it's just everything. Just throw everything at it, because any possible problem we can find before earlier than actual users being affected by it, the better. And I think that makes sense, but I think that to me is it's pretty rare that people have needs that specific. And I think when most people are evaluating what do I think of type checking at runtime versus build time, which is like kind of the big one, or like what do I think of gradual typing, I think it's much more common for them to be assuming that security is something they're thinking about, but not something that they're treating as so critical that obviously they need to throw everything in the toolbox at it. So in some senses, I kind of think of that as well, if you need to throw everything in the toolbox at it, well then yeah, these are all in the toolbox, so throw them in there. But if you don't, then yeah, is it necessarily a compelling reason for people to make decisions? I don't know.
Yeah, I mean, I think too. Yeah, like you say, if you're doing something that safety critical, you probably already know it, and you probably already have tooling that will help you to do that and make sure that you've got everything right. Yeah.
Yeah.
I mean, C is statically typed, right? It has compile time type checking, but in general, it's not considered strongly typed, which is getting into fuzzy words, right? But a lot of safety critical things are done in C, and C is notoriously dangerous, right? So.
Yeah, but I think the main reason for that historically is performance. Is it's like in the case of NASA, it's you have tight memory constraints, and because I'm definitely getting out of my depth of knowledge here, but some things that I've heard are that if you want to have memory that actually can survive in space, especially with all the increased radiation stuff it's getting because you're outside the ozone layer, it's just a lot more expensive, so you tend to have not a lot of it. So you're very memory constrained, and also very performance critical, because if you're not able to fire the thrusters at the right time or whatever, bad things can happen. So because of all that, you end up performance is just a very hard requirement too. So you have an innate tension between wanting it to go as fast as possible, and if C is the the only language you can. I think it's true that well, certainly the original Apollo launching people into space stuff was done with I assume it was punch cards, but definitely assembly language, not any kind of type checking. And I think the moon landing also did, if I remember right. But yeah, I mean, so from that perspective, C would be a big upgrade. But yeah, I mean, by today's standards, it's if you could do it in something like Rust instead, I assume you would prefer to.
It's funny you mentioned that, because I get this email called Excerpt of the Day, and they had a story just a few days ago, and I thought, wow, if NASA had this happen, where they actually had, when the moon lander was going down towards the surface of the moon, they actually got an error, like a 1202, and they had already documented this is not a problem, just go on. But didn't expect to see it like when it was actually landing. And I thought, wow, this is,
Oh, dude, I just watched that documentary again, and it like I don't know why I didn't catch that particular piece the time before when I watched it, but I that blew my mind when I watched it stuff too. It was literally something that like it was doing what it should have done and what should never the combination of those things is what caused essentially a catastrophic event, right? Like things that
Wow.
right.
Yeah.
Right. And I thought to myself, I'm glad to know I'm not the only developer who has this should never happen in production, type of errors,
Right. Yeah. Wow.
I think the other interesting thing about types, while we're on the subject, is it's a way of us communicating our intent to other developers too.
Sure.
Languages that don't have lots of types in them, that's like you say, it's easier to get code out and I hack something together and I try it, but the types can communicate to other developers. I meant to do this with it, or I meant to do that. Whether I did it or I didn't, this is what I meant to do.
Yeah. I think that's actually huge. Like I think one of the things about languages that have types, right? Like Java, right? Things have types, but you don't really use it as a tool, right? For like data modeling, and essentially, it's not nearly as useful, right? Like whereas Elm really promotes, like I had never really designed model first, right? Like setting all that up, and I started to realize like if you get that right, like essentially the rest of it just kind of like comes together. So yeah, I've definitely noticed that it's really valuable when as a tool rather than just as a hindrance, right? It's not in your way, it's helping you to move forward correctly.
Yeah, that's been my experience in Elm, but not as much in like I guess like necessarily in other languages I've used. I think it partially depends on like how the type checker works, like how the type system works. But yeah, definitely that it can be. On the subject of documentation, I did want to keep that. I intentionally decided to keep that out of scope for this talk because you can do documentation with types even if there's no actual type checking. Like it's pretty common in like documentation for JavaScript or Python to be like, this function takes a string and an int and returns a string. From a documentation perspective, it's not checked, so it might be wrong, but it's still communicating the same thing, just in like maybe a different syntax.
Yeah, in code that basically my mentor, even with PHP, right, which definitely didn't have types, especially when I started with it. We'd append essentially a one character like S for string and I for whatever and B for Boolean. And you know what? I'll be honest. Like, of course, it wasn't perfect, but it was pretty freaking helpful, right? Like it didn't get in your way necessarily, but it definitely allowed you to kind of like see what you're expecting, right? Like what the heck? So
yeah.
Hey, Chris C, you're being way too polite, man. Chris C had a question and I just now noticed it and I'm sorry. You should have raised your hand or something. He asked, is Rock based on LLVM and what do you use for a linker?
Yeah, great question. I'm gonna turn on my light here because the sun's going down. So it uses LLVM, but it's not based on LLVM. So we actually have two backends, meaning like things that we use to generate machine code. Oh, that light's very, let me scoot over. So it's marginally better. So we do use LLVM, but we don't use it exclusively. So when you're doing an optimized build, we use LLVM to generate the machine code, and LLVM does its own optimizations after our optimizations. It's great at that. It's slow though. Like LLVM, its whole downside is it takes a long time to generate code, but then once it's done, that code that it generated runs really fast. For development builds, and we only have this currently partially working on, I guess we have it partially working on multiple targets, but whatever. What we do is we go to straight to machine code. So like, for example, on like x86 Linux, and we have like ARM Linux also working, and I forget what we have on Mac OS.
Do you have it working on the M1 chip? That's my real question. Sorry.
Not yet. So sorry, I'm mixing up linking and code generation. So there's like ARM code generation and words like x86-64 code generation, and then there's linking, which is like based on the file formats. It's like the operating systems, like Linux, Mac OS, and Windows all have different. So you have to like deal with code generation and linking for all like 6 of those combinations if you want to support them all. Yeah, so we basically go straight to machine code. Oh yeah, and then WebAssembly also, same thing. We either go through LLVM or we generate our own WebAssembly. That's actually, I think, maybe the most complete is the WebAssembly development backend. But basically, so what we do there is we generate our own machine code, which we can do way faster than LLVM, but it doesn't run as fast because we're optimizing for like feedback loop rather than like runtime performance. So certainly, like if you're like running tests, that's the trade-off you want, I think. And if you're just like doing local development, but then of course, if you're like shipping something, then you want to actually like do the or testing performance optimizations, then you want to use the full like LLVM backend. We also have our own linker, which actually works and is the default on Linux. We're like most of the way, but not all the way done with it on Mac OS. It's not a full linker. It just does like what we need based on, it's like a very rock specific linker. And it takes advantage of a lot of rocks like other design decisions to be able to like both run really fast and also like not need to have as many features as a normal linker would have, like by a lot. And it's super fast. Like linking is also another thing that takes a long time. And we're not, I don't know, partly doing that for performance, but also there's like a bunch of other benefits to it that are very rock specific. So once we finish that up for Mac OS, then like we also have that for WebAssembly, like doing our own linking. So our actually we have a benchmark which I didn't put any slides on, but when we're compiling, I think it's in the talk that I linked though. When we're compiling and running Hello World, we can do it almost as fast as Python in terms of like, even though we're also like type checking and everything and like generating machine code instead of like interpreting it on the fly. We should be able to overtake Python. There's like a couple of optimizations that should get us there that we haven't done yet. Yeah, like the goal is to like compile and run Hello World faster than Python, and just in general to be like really, really fast at like building and running stuff in developer builds. Optimized builds, we're okay with those taking longer because it just takes a long time to like run those optimizations. There's no other way to get the fastest runtime performance, unfortunately. But for developments, like you should not need to be like, oh, code's compiling, like unless very specifically what you're doing is performance optimization, where like you need to run the optimizations every time to like evaluate it. Unfortunately, I thought about it and I was like, I can't see any way around that. It just like with the tools that we've got today, we can't really like make that super fast, unfortunately. But the rest we can.
That brings up a question to my mind, Richard. Do you guys have the ability with Rack to have certain constructs treated as warnings as opposed to errors, so that, and then someone could say later on, maybe I want to treat all warnings as errors?
So yeah, so the way that we do that is, so on the slide that I showed the screenshot, anytime you have any errors or warnings, it says like you can run, rock run to run it anyway. Warnings, so the distinction between warnings and errors is, and we do have one, is that warnings basically mean there is no chance this will cause a problem at runtime. Like it's not going to break. It's just like, FYI, you should probably deal with this, but like it's not going to break anything, but like you should deal with it. Error means your program might break, so if you run it, it's risky. But both of those return a non-zero exit code. So the idea is that like on like CI, for example, like it'll break your build if you have any warnings or errors. It won't block you, but it will say like you need to fix all of these before you get a passing build.
Excellent.
So that's just how we do it. Yeah.
Yeah. I mean, I remember a couple of years ago, the heartbleed bug was down to, it wasn't even like, it wasn't something that even a linter would catch because it was legal C code. It was just that they had to put curly braces around that one block.
Oh yeah.
And it's like, wow, that is really some.
Yeah. That's
really amazing to me.
Yeah, I mean that's just a syntax choice on C's part that I don't think was a good one in retrospect, with the benefit of hindsight. But yeah.
Anyone else? I apologize. I've been kind of monopolizing the talking because I'm enjoying this talk so much. But anybody else have any other questions? Please don't hesitate. Jump on in.
You don't have
And
a
Richard,
question.
are you? Oh, go ahead. Yeah.
I was just gonna say, I just have a comment that the fast feedback loop is something that I'm feeling a lot because I'm doing Rust stuff and I love the type system. I love the, how safe it is and stuff, but it's not like Elm. You're building an Elm and it's just like,
Right.
it's
Yeah.
to have both options. It is pretty sweet. Pretty excited about that.
Yeah. It is honestly exciting to look at this and say, I see that they solve some of those pain points, right? I did have a question. So with Rock, does it have any kind of like a I hate using the word design pattern, but essentially anything like T where, like Elm architecture style stuff where you have commands and, is it essentially as immutable and pure as Elm is, or have you done made some different choices there?
It's as immutable and pure as Elm is. There definitely are some differences, I think, in the patterns that will emerge, largely because of Rock's platforms and applications design, which kind of out of scope for this. It's like a whole rabbit hole.
Okay.
But one of the really critical things that I think if someone were going to make, and I know because I need to sketch this out because of some Rock projects we want to do it for desktop applications. But if you're doing a graphical user interface in Rock, I don't think it's like a slam dunk obvious thing that you go for Elm architecture because you can't quite do lazy the same way that you can in Elm without adding an extra type variable to everything. The only reason Elm's able to do that is because with the type system that Elm and Rock both have, is because it sort of cheats with kernel code, but we don't have an equivalent to that. So you couldn't quite do lazy that way. But there's another important difference between Rock and Elm, which is that we don't actually use persistent data structures. We do opportunistic in-place mutation behind the scenes, which again, without going into a whole lot of detail about that.
Right.
Yeah. Basically, it affects which data structures we use, and which also affects which optimizations are good. And so I'm actually skeptical that lazy would be that good of an optimization in comparison to some of the other things that we could do. So I came up with an alternate design, which has some things in common with the Elm architecture, but also some very notable differences. Definitely has trade-offs like pros and cons. But I think it seems like, especially from a performance perspective, it would make more sense for Rock. And so that's probably what's more likely to take off, but we'll see. I haven't actually implemented it all the way and tried it out yet, so it's on the list, but
sure. Do any of I jumped onto the Rockling website and basically has the talks and whatnot. Do any of the talks go over any of the basics of going through the structure of a Rock app and whatnot? I'm guessing they do, but
yeah, so there's one that's called A Taste of Rock, and that's basically just kind of an overview of the syntax and the type system and stuff like that. And it's not comprehensive, but it's I think you get a good idea of what's going on there from that one.
Okay, cool. Thanks. Yeah, no, that's what I was wondering.
I don't think there's an open source project in the world that couldn't use someone to help. Here's a tutorial. Here's how you start.
Yeah,
the hello world of every open source project.
There is an actual tutorial in the repo, but I mean, right now, I mean, it's as of today, it's you have to build it from source, and there's plenty of paper cuts and stuff lying around, and we're really focused on the big goals and making sure that and validating that these high level approaches work. So there's a lot of lack of polish in a lot of areas right now, but we actually have multiple people working on it full time now, which is very exciting. So including me. As
awesome.
of April. So
cool.
That's we've made a lot of progress already in a month and a half, and I'm very excited to see where we are by the end of the year.
Wow, a month and a half, really? With the team working on it full time, or wow?
Yeah, we've had since April 3rd, we've had multiple people working on it full time.
That's super exciting.
That's awesome.
Cool. Congrats, man. Yeah, that's
good
stuff. Good stuff.
Yeah.
Awesome.
I find it really interesting. I don't know about anybody else, but I find it really interesting to hear how the sausage is made when you're building a compiler and stuff. Because, I know those decisions have to be made. Do we do this way? Do we do it this way? But
for sure,
I'm not always clear on why somebody picked a certain way.
Yeah, I mean, I think like this is my thought process. I can't speak for all compiler authors, obviously. Lots of people think about things in different ways, but also like I know that in a lot of cases people are not thinking about it from scratch. It's more like I want to get into the like JVM ecosystem or the JavaScript ecosystem or the Erlang Beam ecosystem, and like they're starting with that as a premise, is like I want to like be in this world, and you just inherit a lot of these design decisions like from that. Like, maybe you're stuck with like runtime types because the Beam needs runtime types. Like you have no option to like get rid of that. But maybe you can like do stuff like, okay, just at the edges I'll generate them, and like internal to my own stuff I won't do that, and like only when I need to talk to like other things on the Beam. I don't know. I've never built anything for the Beam, but yeah, I think it's definitely like from my perspective, I because I was like, okay, for this language I have some like design goals in terms of like ergonomics and stuff, and I'm just kind of stepping back and saying like, we're doing everything from scratch. Like, how do we achieve these goals? And like, this is what we came up with. Saw a question, focus on build times reminds me of Guy. You looked into that language from Jonathan Blow. I'm aware of it. I have not used it. So I know that it has, and I think it's closed source, is like a closed beta or something. So like you in order to try it, you would need to like get approved. Rock, you can download the source code from rocklang.org, but right now the repo is closed. So like if you want an invite to the repo, you just have to like email me, rock at rtfeldman.com, and then I just give you an invite. Like there's no approval process. It's just like literally just ask for it and then I just add it. And we're just doing that to like really clearly set expectations of like, this is not ready for production use yet, like which is super isn't. But we're actually planning on like opening up the repo like in a matter of months. Because I think, well, fingers crossed, we think it'll be like far enough by then that like it'll be okay. But anyway, so yeah, I have not tried it, but I have heard of it. And as I understand it, yeah, it's like it's also a systems level language, but it's like got a focus on game programming, and it's designed to run really fast and also to compile really fast. And I believe it also has an LLVM backend as well as a straight to machine code backend. I think that's true. But yeah, I mean that kind of seems. I don't think it has its own linking though. I think it does. I think it uses like a system linkers. But yeah, I mean, I think that's like kind of the best way to balance the desire for like really fast runtime performance in like optimized builds, and then also really fast compile time performance in development builds.
I'm glad you ended up talking about Rack, because I'd seen your talk down at Strange Loop and I found it really interesting and I wanted to hear more about it. So I'm glad you ended up talking about that.
Nice. Yeah, there's other talks on the website. I've kind of gotten into like I don't know, various different aspects of it. But yeah, it's like I've kind of been trying to take an approach of like simultaneously like spending most of the time working on it, like actually developing the language, but then also just sort of like oftentimes I will come up with something where I'm like, I want to explain this like design decision or like this cool thing about Rock, but like it requires a lot of buildup, and so I end up making the talk primarily about the concept as a whole, and then like I at the end or in part of it I'll just like incorporate like, and here's what we do in Rock. So it seems like kind of a cool way to like, I don't know, balance talking about it without just going on and on about Rock for for however long.
No, it's very cool. I'm glad you did, because like I say, what I saw down on Strange Loop, I was like, that's really intriguing. The only reason I'm not looking at it is because I have way too much shiny new object syndrome. So
well, also I would recommend, if you're looking at it right now, it's it's very, it's a construction zone right now. So yeah, it'll get more polished though. I mean, and it's like even like way better than like I gave that Strange Loop talk at like September, like back in September. It's already like way fewer sharp edges and problems with the like compiler bugs and stuff than it had back then, and it does more. But definitely need quite a few more cycles before it's like, okay, I'm very strategically showing you screenshots of things that already work nicely, but there's plenty of things that don't yet,
Yeah, I was going to ask about community, but I'm like, no, we don't want to distract them. Like, yeah.
Yeah. Oh, I mean, there's already we have like a monthly meetup of like people like who are into Rock on the like
oh,
Rock.
Cool.
So, yeah, if you want to get in on that, just like, there's a link in the README. But,
Perfect.
yeah. Well, there's a link in the README to the Zulip, and then in the Zulip, there's a little like gatherings thread where we just like every month I just put up a like when to meet, and people just fill out like, here's when I'm available, and we just like find a time when the most people are available and just like do a call. And we usually like talk for,
like low
hours.
overhead, because like community, like really building a community, right? Like that's just so much overhead. You don't want to do it at an early stage like that. So, but that sounds cool. I'll check that out, Richard.
Yeah. All are welcome.
Yeah, like I say, when I saw that Strange Loop talk, it was like, oh wow, here's like a system language, or kind of becoming a system language, but it's got those awesome Elm error messages, and this is terrific. I love this.
Yeah, I mean, I think like I wouldn't go as far as to call it a systems language, just because I don't think you would actually implement an operating system in it. But definitely in terms of performance, we want to compete with systems languages. Like even knowing that we'll never catch them, it's like we're always looking at ourselves like, not in terms of like, how do we be faster than Java? Yes, but mainly we're just like, why are we slower than C++ in this area, and can we get closer to that? Is there some way we can catch up to that? And sometimes the answer is just absolutely not, because doing that would require either manual memory management or like lifetimes or something like that, like Rust has, neither of which are like bridges we're willing to cross. But it's like within the confines of like, we have like reference counted heap memory management. How close can we get? And quite often the answer is very, very close. But not all the time. That's okay. That's the trade-off we're willing to make.